country and able to keep the final two lectures. And should be focusing on human and partly archaeological records which provide indicators of climate change, interesting stories that emerge from understanding elements of prehistory. What I will do today is say a few words about some of the intermixing of, I guess, science and politics in the study of climate change, and talk a little bit about publication, and then finally say some words about the final exam. So, I don't know how long today's lecture might last. It might last 15 minutes, or it might last the full session. We'll see how it goes. One of the things that people sometimes show are images like this. I took this photograph some time ago in southern Vietnam, and it illustrates an example of coastal erosion and due to rising sea levels. So you don't normally expect to see palm trees growing in this fashion on the beach, and clearly it's an expression of more recent sea level rise and coastal vulnerability. Of course, Colin Woodrow addressed that topic a few weeks back. One of the things that I think hopefully you're aware of by now, with the reflections that you've made in this subject, is that there's a huge literature on climate change, not just in scientific journals, not just in the media that you've touched on with these exercises, but also in the forms of formal books. And I did draw your attention to some of these books earlier in the subject. Since I last saw you, I came across these two books that are very interesting, and I thought I'd draw them to your attention. The one on the left by Guy Vince is an interesting book. It's nearly 500 pages. I'm still wading through it at the moment. And it's of her exploration, journey around the world, looking at how climate change is expressed today. It's an unusual book in the sense that it's not all doom and gloom. It actually looks at how people are responding to more recent climate change. So, for example, people trying to make artificial glaciers so that they can have water supplies to grow crops. So, for example, in Tibet, where some of the ice sheets and glaciers are melting, people are actually trying to produce artificial glaciers that will provide just enough water for them to continue to live in the region and grow crops. The book on the right-hand side is an interesting work, similar amount of pages, in the order of about 500 pages. Both these books were published this year by John Brooke. And what he's doing is looking at the history of us, we humans, and how we came on the planet, and how climate has been a significant consideration in terms of human existence. And so it reviews a very long history, if you like, and it's written, he's a historian, social historian, so it's a very different approach. And should you come across this book and flick through it, you'll see that it's written in a form that could easily be regarded as a science book. There's lots of graphs, and it's very quantitative, but an interesting read. So the one on the left-hand side is one that is written in a more easygoing, laid-back fashion, but it makes lots of interesting points. And the way the book is structured, there are each chapter has an introductory section that gives very detailed information, quantitative information, and then it goes on to her own experiences as she travelled. So in terms of subject overview, what we've tried to do, firstly, examine some fundamental concepts in climate science, and in particular to consider what are the drivers of climate, both natural drivers, so what are the forcing functions, solar variability, the long-term scale, we looked at Milankovitch forcing, the change in the orbital configuration of the planet, and that's a very significant topic. And it's of interest because, of course, the Milankovitch model, which was then subsequently supported through studies of marine cores, deep sea cores, and also ice cores, showed long-term variability in climate. And the importance of those studies was that it really started to give a fundamental insight to the sensitivity of the planet to long-term climate change, and particularly the relationship between the abundance of CO2 in the atmosphere and Earth's surface temperature. Now, there are articles, and there was a program last week in Catalyst that spoke about so-called hidden heat, which is an interesting topic because it brings into consideration variability in temperatures on the surface of the Earth and heat budgets and where's the heat going. And that's another topic that is of interest in terms of climate drivers. We looked at teleconnections. Remember, teleconnections, what's happening in the eastern Pacific affects what's happening along the coastline of Australia, along the western Pacific. So there are teleconnections and, of course, oscillations. So Tim spoke in more detail about El Niño, southern oscillation together. So these are fundamental climate drivers, and they explain some of the variability in the climate system. And I think one of the things that we really want you to get from this subject is an understanding of what variability means and its impact on understanding longer-term trends, deciphering longer-term trends in climate. It's a fundamental thing. So, for example, what was discussed last week in Catalyst and what was discussed in weekend newspapers about the so-called missing heat relates to the topic that some people are suggesting, well, perhaps in the last 18 years, perhaps Earth's surface temperatures haven't increased as dramatically as people had originally thought. And again, this all relates to this notion of looking at longer-term trends, looking at variability in the Earth's climate, and understanding what's happening in the longer record. So, secondly, one of the things we've tried to emphasise in this subject is the historical context of climate change, and that's why we reviewed a lot of the earlier records, the pre-instrumental records. Remember, we looked at proxy data, so indirect indicators of climate change, records from peat bogs, tree rings, corals, etc., speleothems, many different indicators of changing temperatures and climate. And as I've said, that historical dimension, without that historical dimension, we really wouldn't have a clear sense of what's happening today. And then those analytical approaches that I've just mentioned. And then, of course, the last 1,000 years of interest, and some of you have tackled that with that essay in terms of looking at the medieval warm period and the Little Ice Age, and reflecting on what those subtle differences in temperature, how they were expressed on the surface of the Earth, and what it means in terms of what's happening today. And we looked at curves. I've deliberately, not for the purpose of this lecture, taken many curves that I showed you earlier in the subject, simply because that would detract from other things that I want to talk about today. But just to remind you that in terms of scales of observation, we can see more detailed trends if we hone in at higher resolution. And this is an example of a very generalized. It looks schematic, but it's based on really real data from Rudderman's book, Bill Rudderman's book, which looks at changes over different periods of time. So on the left-hand side of the graph is the so-called tectonic changes, and what we mean by that is changes in climate that ultimately really have a tectonic cause. So the and I did discuss this earlier in the subject, well, really very early in the subject actually, looking at how, for example, plate tectonics can surprisingly impact on climate. And it did that, for example, with the closure of the so-called Isthmus of Panama, that gap that formerly existed between the North American continent and the South American continent. When that happened, 3 or 4 million years ago, it meant that the world ocean circulation changed. Similarly, with the collision of the African continent with what is now Europe, that also led to a change in ocean circulation, quite profoundly. So that's an example of tectonic changes. Then, of course, the orbital in B, the second left-hand image, orbital changes due to the variations of the Earth around the Sun, which brings about deglacial climate changes, and then ultimately looking at the more recent historical record. So what does climate change mean? Now, this is an interesting book that you might like to follow up. This looks at the expression of climate change, particularly in the context of water. So it has the subtitle Water Worlds, so living with environmental change, water worlds. I'm not going to read out the text, but suffice to say that, and I've selected 3 examples here. These are, if you like, interviews that a contributor to this book made, and they illustrate different aspects of climate change. So one obviously is sea level rise, coastal erosion, and seeing large trees like this exposed on the beach. Now, one could argue, well, is that due to a sea level rise or some other subtle changes in the coastal system? To address that question is not actually that easy. But she makes other observations about changing groundwater levels and how that's impacting on the growing crops. In this case, in Africa, in Burkina Faso, which is in West Africa, and Hamadu, he's talking about changing temperatures, the fact that it's noticeably warmer than it has been in the past, and also the fact that mosquitoes, it's not possible to sleep out in the open, but they're affected by mosquitoes where they weren't in the past. So the notion that climate change is expressed in a variety of ways. Gaia Vince, in that book that I introduced to you, that was published this year, where she travels around the world, comments on this topic as well, in terms of mountainous regions that are suffering major problems in water supply, and there's a case study here where the person is commenting on the fact that there's problems in water availability. What he's doing there is controlling water for the local community, for those that have rights, local water rights for irrigating their crops, and this is in Peru. So there's a lot of interesting case studies that are illustrated in this book about how climate change is manifested. And so it's obviously affecting many different aspects of people's lives. So this is another book that I'd like to draw your attention to. It was published a few years ago, back in 2008, and it looks at science and politics of climate change. And some of the subsequent images I'm about to show are based on the reading of this book. The so-called climate change debate. The first thing, before I refer to these 3 points that are in italics, first thing I want to draw to your attention is that science doesn't have debates. If you think that, you need to think carefully about how science works. People don't have debating contests in science. It's not a case of generating an argument that appears to be more persuasive and therefore you get more votes. That's not how science works. So the the point that I'm trying to make with this is that the word debate is actually, and it's popularly used in the press, it's actually a misnomer. Science doesn't work that way. And we'll go into in a minute how science does work, and I'll remind you of that from those earlier lectures in this subject. So anyway, the so-called climate change debate, fundamentally an argument over these 3 points. And I think that if you reflect on the readings that you've done in the journals that you take, you're probably aware of these points. So how should we respond to climate change? You can think about that in your own minds. You can think in your own minds in terms of how governments of the world have responded or continue to respond. And this is an interesting question. The second question is sort of based on almost a cost-benefit analysis, and some environmental problems are tackled in those terms. So the risk of polluting the area, is it justified, etc. So do the risks it poses call for action? And how much effort and money should be expended? Okay, these are very, very challenging questions which all governments of the world face. Those comments, those questions, need to take into this point the term positive and normative claims. Okay, so positive and normative claims. And I'd encourage you, in terms of your continuing development of skills in critical thinking, to think about this, particularly whenever you read articles on the subject of climate change, to think about what are the statements that are positive statements. And I don't mean positive in the sense of good, as opposed to bad, positive and negative. I don't mean that. I mean positive statements, so as I've written here, a positive claim is a statement that we know without ambiguity. And I've written some examples here. So the state of affairs. You go outside, is it raining? You know, you have that empirical experience of getting wet. Okay? That's a positive statement, it's a positive claim, it's a factual statement in other words. A positive claim can comment on trends, the winters getting warmer, as we saw with that case study earlier of a gentleman in Africa commenting about summers getting warmer. Or a causal relationship. Now, cigarette companies will still say, probably still argue that smoking doesn't cause cancer. I think it's fair to say it does. So causal relationships, positive statements. So we can make a positive claim or statement, also a positive question. So a positive question, and these are the sorts of questions that lawyers will ask in court. And you'll be asked to respond either perhaps by yes or no. So give a very factual answer. Okay, so a positive question has a unique solution. But it has to be, and this is this caveat that I've written here, it has to be carefully worded. So you don't want to, if you're a barrister, you don't want to ask a question where you're not going to get the answer you want. So you ask it in a very specific manner. So it means that one's wording has to be particularly careful. And so the answer is not contingent on political ideology or religious beliefs. So a positive question, and please remember that I'm not talking about positive and negative, but as a statement, positive question is not influenced by one's ideology or fundamental beliefs. What about normative claims? A normative claim involves a form of evaluation. So a normative claim, a form of evaluation, not how things are, but how they perhaps should be. might be something that's idealistic. So the notion that something is good or bad would be a normative claim. So it's something where you've made an evaluation to reach that conclusion. Or right or wrong, desirable, undesirable, just or unjust. So these are normative claims. And what you might like to do is perhaps look what you might like that someone set their alarm clock so they can actually now listen to my lecture. Time to wake up. What you might like to do is try this out. Next time you read a newspaper, or get on the web and look at crikey.com or whatever. Evaluate the article. Look at each sentence and think, is it a positive statement or is it a normative statement? And so you look for words that I've written here in italics, for example. So examples of words that are indicative of normative statements include should or ought. Normative question, shall we raise the tax on cigarettes? So the final point here is that normative questions are more deeply contested than positive questions. A normative question is going to generate a lot of discussion, whereas a positive question will be a straightforward answer. Is everyone happy with those principles, those ideas? All right. So the problem then with a lot of literature in terms of climate science and the study of recent and potential ongoing climate change is the tangling of these two types of sets of words and statements and questions. So Dessler and Parsons state this tangling of positive with normative claims and of explicit arguments with powerful unstated assumptions, I'll get back to that in a second, obstructs reasoned deliberations on policy decisions. It exacerbates, in other words, makes worse, conflict, makes it difficult for citizens to form, come up with an informed view. Okay. I think you'd all agree that the study of climate change is unquestionably a complex topic. You'd agree with that? And hopefully what we've tried to do in this subject is not preach, but actually let you come up with what you think is happening through your development of critical thinking skills. So in terms of trying to help you with that notion of critical thinking skills and commenting on positive and normative statements, the term that is also an important term to underline here is the term unstated assumptions. So sometimes people like to ask a question with an unstated assumption in the question. So it makes it a very loaded question, and therefore leads to a lot of debate and discussion when perhaps deep down the question is simpler. Well, I want to move on to that to say a few words about how science works. Okay. So science is a process that advances our collective knowledge. You're all aware of that already, I think. I don't need to really emphasize that point. But it does that by proposing and testing positive claims. So, in other words, establishing hypotheses, and we'll get to that in a second. Science is a social activity, meaning that it's not just one individual that's undertaking research, it's many individuals from around the world. And one of the things about science is that it strives for consensus. It doesn't strive for conflict. And at one level, that could potentially be an interesting distinction between science and humanities. So in the humanities, And I did introduce this notion in the very first lecture. There are different theories that are used in the humanities to analyse ideas, analyse aspects of history, analyse, for example, societies, how societies work. And that's a very different approach to science, where science uses an empirically based approach and strives for consensus. You understand why that's important? Think about it in terms of flying from Sydney to London. You would really rather hope that there was some consensus in terms of principles of physics, aerodynamics, aircraft construction, navigation. If there wasn't, if it was multiple worlds and anything could go, anything was valid and relevant, it's very likely the aircraft would fly out and crash. So, in that sense, the notion of consensus is very important. So the logical structure of scientific inquiry we've covered before, but I just want to just remind you. So formulating a hypothesis, or plural hypotheses, reasoning about the evidence that should be observed. So you're anticipating some of the evidence to evaluate the hypothesis. And in the sense of that, anticipating that evidence enables you then to construct a better hypothesis and then test it. And then, of course, testing the hypothesis and ultimately trying to see whether it stands up or whether it doesn't. If it stands up, it might be a good explanation, but it still might not be the best explanation. So remember that. And of course, in terms of the way science works, it's more common to refute and dispute and negate hypotheses than to supposedly verify them. And in that first lecture, or second lecture, introduced you to those two approaches to science, the deductive approach and the inductive approach. So there are two approaches that are used for collecting scientific information, and they're both valid. They're just different ways of approaching science. So one is the inductive approach, or bottom-up as it's called, whereas there's the sort of unstructured collection of data, and then it's classified, facts are organised, inductive generalisations are made, and then ultimately some kind of law or theory is constructed. Perhaps that approach might have, if you're looking for an example of that, on a rather grand scale, the formulation of the theory of seafloor spreading, and ultimately continental, not continental drift, sorry, but plate tectonics, the separation of continents, etc., is a classic example of that. It started out by people after the Second World War surveying the ocean floor, collecting data, collecting rocks from the seafloor, dating them, collecting magnetic anomaly data, and then piecing all that together. That was really a classic example of this inductive approach. It didn't start out, people didn't do it from the perspective of setting up a hypothesis. Whereas the deductive approach, you have some idea of an explanation for a particular set of observations, and then you try to test it. So it's the structured organisation phenomenon. And you may select several hypotheses and see which stands up. Okay, so those two contrasting approaches. So hypotheses are rejected more decisively than they're supported. It's just the way science works. And please remember, and I don't want to preach now, but please remember the difference between a hypothesis and a theory. Because have you ever heard people say, in theory it's such and such, meaning that it's equivocal? No. Theory is why you're sitting down on your bums there right now, rather than floating up in the room because of the theory of gravity. That's the theory. It's not airy-fairy, it's sort of factual information. So, I've already stated this really, philosophically and practically science strives for consensus. When there is a strong scientific consensus on some positive point, remember positive, not normative, positive in the sense of factual information. Those outside the relevant scientific community who care about the answer can do no better than relying on a consensus. So that's an interesting idea. Of course, the difficulty comes in then trying to implement government policy, and I suspect you can appreciate why. Well, let's talk about the peer review process, just a few words. I thought I'd say a few words about this because it's something that comes up in terms of climate science and notions of Machiavellian ideas that some people were lucky to get a paper published because Joe Blogg's supported an argument, etc. What is the peer review process and why is it important? So peer review applies to everything that's published in academic journals. It doesn't apply to newspapers, and so there's a warning sign straight away that what you read in the newspaper should be read with caution, not necessarily regarded as gospel. However, I should make the point that to some extent applies to journals. Everything you read, you should always be questioning, okay? Because it looks impressive and it's in black and white in print. You should nonetheless question it because things do creep through in journals as well, and that's why sometimes you see in journals so-called correspondences and replies where people have written in and criticised the paper that was published because they hadn't considered some aspect in the interpretation of their data, or they weren't aware of something that was previously published that had a significant bearing on what they were suggesting. But in terms of the peer review process, what commonly happens, this is a journal that I've been editing for quite a number of years, and it's a big journal. This journal, we receive about 600 papers a year for evaluation. We publish 28 issues a year, and in terms of the print run of pages, it's about 4,500 pages. So it's a big journal. So the manuscript is submitted. It comes to the editor, and they'll look through it and see whether it is falling within the scope of the journal. So, as an example of something that we received, we received some crank manuscripts from time to time. One about biblical flood came in a few years ago, where a person had used Google Earth and supposedly identified shorelines relating to the flood. That was rejected. But there are also articles that are submitted that aren't appropriate for the journal, because they don't really fall within the scope of the journal. So there's that aspect. And then, of course, there is an interesting element to it in terms of selecting papers. Some might not be topical. There is a business aspect to publishing, which is an interesting thing to reflect on. So some journals are trying to out-compete, or not out. All journals are doing this actually, competing with one another, trying to get better copies, better papers. And so there's a competition there between journals. And all journals have impact factors, so how well cited the works are, and that attracts authors. So a high impact factor journal will attract contributors, and people will be less inclined to publish in a lower impact factor journal. So there is a political, what I'm trying to suggest now is that in terms of the world of publishing, there is an interesting political dimension. Scientists are competing with one another. Scientists who are working on topics, will be the specific topic of climate science. There will be many people around the world working on the same topic, and they'll be trying to outdo each other and get priority in science, because that's how people become famous, how people get promoted, earn lots more, potentially more money. So there's that competitive aspect of science as well. So when a manuscript comes into a journal, it's assessed for whether it's appropriate for publication in the sense of the scope of the journal, whether it fits into the sorts of papers that should be published in the journal. When I say should be, so an obvious example, someone sending in an engineering paper relating to the transmission of water in pipes wouldn't be appropriate for this journal. So it's clearly rejected. That's whether it should be published or not. If the work gets past the senior editor, then it is sent out to another editor who may handle the manuscript, and then they send out the work to reviewers who comment on the scientific merit of the work. Now, generally it's 2 reviewers, sometimes it can be more, and this is where the sort of wisdom of Solomon arises, because sometimes you get a manuscript back, peer evaluation indicates one person recommending publishing, and the other reviewer recommends rejection. What to do in a situation like that? And in terms of the dynamics of publishing, there are some people that have got a sort of a thing about not seeing Joe Blogg's papers published, so it's sort of a personal vendetta, and sometimes editors have to work out, well, is that part of the dynamic? Is that part of the problem? So the peer review system then is such that people generally write fairly lengthy reports in terms of how the manuscript should be improved. And it's not just in terms of spelling, but it might be experimental design, it might be that people have to go back and do more bench work. So the types of comments that can be made can vary significantly. And then ultimately an editorial decision is made. Now with a high impact journal, many manuscripts are rejected if there's a dissenting view. If there's a slightly negative view and there's a high impact journal, then the work is very likely to be rejected. Sometimes though editors make a decision, normally I'd reject this paper, but I think that there's some value in this paper and it has an important message, so I'm going to encourage the person to revise the work. So there's that latitude. It's the editor that makes the final decision, not the peer reviewers. The peer reviewers make some sort of commentary on the science and whether the science can be improved, but ultimately it's the editor that makes the decision. And the decision is made sometimes on very complex reasoning. Now, why am I discussing this? Well, the peer review process has been criticised and has been the subject of scrutiny in climate science. And there are many examples where people have commented on that process, particularly in the context of politics. So I simply made all these points really to draw your attention to how the publication process works. Now, in terms of what you read, as I said, and I've encouraged you in the past, not to necessarily accept everything that you read. And there are 2 contrasting books that I wanted to bring to your attention here. One was the controversial book published by Ian Clymer called Heaven and Earth, Global Warming and Missing Science. And then Tony Eggleton's book, A Short Introduction to Climate Change. This was published a few years ago by Cambridge. And it's an interesting book, actually. It tries to really dispel some of the myths about the skeptics that are at times misrepresenting climate change. And so in the next image, it's taken from Tony Eggleton's book. So always scrutinise the graph. In the top image, you can see the IPCC prediction. This is an image from Pliner's book, the cover of which I showed you in the previous slide. And it illustrates the point of the importance of looking at longer-term trends. And it also gets you to think about how images were constructed. So the image on the left, and these two graphs are from Tony Eggleton's book, which I've put the details down and showed you the cover in the previous slide. So they're from his book, but the example on the left at the top is from redrawn or reproduced from Pliner's book. And you can see that Tony Eggleton has put a star here, and this reflects the 2008 value for temperature, so annual temperature anomaly, and that's where it was in 2008. But what's been done inadvertently or deliberately, I don't know. That's perhaps only Ian can answer that. Is that this line here seems to convey information that it shouldn't have been drawn there. So that the graph really should have been over stopped here, but it was extended here. And then, of course, if that was removed, it has an important bearing on the structure of the data, even for a small time set series like that. And of course, this is the longer record of factual observations, and you can place then the 1990 record through to 2010 on this graph, and you can see where it fits. And of course, this does reflect sort of annual variability in the record. And so I've tried to make this point once before, that in considering recent climate change information, you do need to take the approach that mathematicians do in terms of spectral analysis. You need to understand longer-term trends. And when I spoke earlier, in one of the earlier lectures, I made the point that what a lot of the records do in terms of careful analysis of data is to look at a 30-year trend, say from 1950 through to 1980, and compare that mean with the mean over, say, the past 20 years or 30 years. Okay? So you really need to look at the average data, because there's a lot of variability. Okay? And that variability is an expression, it's a direct expression of the complexity of the global climate system. So complexities that relate to solar forcing, volcanic eruptions, short-term variations in sea surface temperature, etc. And then Eggleton also shows this graph and shows how the scales either inadvertently or intentionally are different. So what it's showing is the image that sort of the reconstruction of Pliner's figure 4 zigzag line. This shows the straight line is the mono-lower increase in CO2 trend, and the horizontal axis, the dates in the upper row are correct. Okay, so that's the upper row, but these are the dates in Pliner's book. Okay. So again, it's when you look at graphs like this that are published in works that are clearly intentionally polemic, and you can make an assessment of whether they're controversial or polemic by reading Dust Jacket, reading the introduction to the book. You'll get a sense of whether it's a carefully prepared work or whether it's trying to be controversial. It doesn't hurt to compare graphs from one reference source to another. So always scrutinise the graph. Okay, well, let's just say a few words about theory exam, and then we'll call it a day. So theory exam is well, it's money for January, so it's not meant to be too taxing, and that's why it's a 2-hour exam. The first part of the 2 sections of the exam, section 1, multi-choice questions, so there's 40 multiple choice questions, and remember that we're trying to select the most correct answer, that's the intent with multiple choice questions. Do answer them all. There'll be a multi-choice answer sheet that you'll need to fill in with a pencil, preferably a 2B pencil if you've got one. And then part 2 are short answer response questions. So you have to answer 6, and there's 8 questions. So short answer response. Don't rewrite the question. Just make sure you number it carefully at the top of each page. If you rewrite the question, you're wasting time. The short answer response questions are each worth 10 marks. So the part B, the second part of the exam, is worth 60 marks, and part A, the first part, is worth 40 marks. 2-hour paper. And it tries to cover a reasonable content of the subject, so it covers pretty well all the topics of the subject. Does anyone have any questions?
So the content that's in the exam, was that pretty much what you covered in the subject review earlier on in the lecture?
No, the whole subject. So what I was doing in the subject review, the intent of that was really to remind you a little bit about the philosophy of the subject and what we were hoping to achieve.
Mm-hmm.
And yes, those topics are covered, but effectively everything that we've covered thus far. So next week's topics, I'm reluctant to say aren't an exam on the archaeology, but that doesn't mean we shouldn't come to the CAT's lectures. So that's what I'm reluctant to say. But pretty well everything else is covered.
Okay, cool. Is there a practice exam or a past paper or something they can look at?
No, there isn't. No. And this is the first time that I've taught this subject, and it differs to last year. Mm-hmm. So there isn't a past paper.
All right.
Any other questions? All right. Well, good luck. If you've got, I'll try and have those essays for you next week. I'm sorry about the delay. And if you haven't collected your journal, please do so now.